Okay, so we are going live.
একটা মিনিট, দিগন্তরাকে বলছি যে ওই যে অঙ্কটা বললে তখন ওই ইনমোর, ওটার উত্তর কি 546?
হ্যাঁ, আই গেস একবার চেক করে নে।
ওকে, মানে রিকারেন্সটা 2 × 3 পাওয়ার n - 2 প্লাস an - 2 এরকম এসেছিল।
এক্স্যাক্টলি মনে নেই, তুই একবার ইউপিএসসি দেখতে পাবি, দেখ।
দেখে নিচ্ছি।
I think we are live. Okay. Can anyone speak? I just want to ensure my sound system is working correctly. Sorry, continue. Hello, can anyone speak? Hello. Yeah, now I can hear you. Okay, so shall we start?
You might as well.
Okay, so here we are. So we thought about giving you all a demo lecture for the workshop 2022. So we have here Supratik Bosu and Orko Sinha, Diganto Bhattacharya and Jyotishko Rai Chaudhuri and also Shoutim Dash. And so they are going to give you short demo lectures on how the actual workshop is going to be. So please stay with us and so Supratik Boshu will be starting first. So yes, Supratik, so can you just say what you will be starting with and what?
Yeah, so since I will be teaching combinatorics in this workshop, so I thought I should start with one or two combinatorics problems. So
Okay. Let's one by one just give an introduction of what we are going to teach today. So Orko Sinha, can you?
Hey everyone, I'm Orko Sinha. Today I shall be doing a problem from past ISI paper on calculus.
Okay. Shotim or Diganto? Yeah, Shotim is there.
Hello everyone, I'm Shoutim. Actually, I'm going to teach algebra in the workshop, but today I'll actually give you a problem of geometry.
Okay, that's nice. Diganto?
I guess Jyotishko will teach first, and if time permits, I'll do some problems on number theory.
Fine. And Jyotishko?
Yeah, so hello, I'm Jyotishko, and so I shall be teaching calculus in this workshop, and probably today I shall be covering some problem on calculus or number theory.
Okay, thank you. So Supratik, we shall start with you. So I'll be making you host. So yeah, Supratik, you are the host now, so you can share your screen and start.
First, we will be looking at this problem, and if time permit, maybe one more.
Yeah, so just share your screen. So you are the host now.
Is my screen visible?
Yes, absolutely.
Yeah. So let us start with this problem that there are 4 basketball players. And they are named A, B, C, and D. So initially the ball is with A. And in each pass, the ball is passed from one player to a different player. So the question is, in how many ways can the ball come back to A after 7 passes? So, for example, say initially it is with A. So A passes to say B, B passes to say C, C gives it to D, D to C, C to B. How many passes is that? 1, 2, 3, 4, 5. So B gives it to say again D, and then D gives it back to A. So A will be the starting point and the end point. And in between, the ball will be passed to a different person every time. So for those of you who do not know, this problem was asked in INMO 2015. And so this is the entire problem statement, that there are 4 basketball players, A, B, C, D, and initially the ball is with A. Every time the ball is passed to a different player, and in how many ways can the ball come back to A after 7 passes? So we will be adopting a recursive approach to solve this problem. So for example, we were asked to find the number of ways the ball can come back to A after n passes. We denote that by an. An is the number of ways the ball can come back to A after n passes. So here we have A, at the end we have A, and in the middle we are making n passes. So after n minus 1 passes, the ball ends up with some player X who is not the same as A. And before that, in the first n minus 2 passes, the ball ends up with some player Y who is not the same as X. But notice that Y might be equal to A. So we might as well divide our problem of finding an into 2 parts. Case 1, Y is equal to A. So if y is equal to a, then in how many ways can the ball end up with y after n minus 2 passes? That is a n minus 2. So the ball can end up with a after n minus 2 passes in a n minus 2 ways. And for case 2, oh, by the way, I forgot to mention that after the ball ends up with a, and we have to fill up x. So x cannot be equal to a, but it can be equal to any of the other 3 players, B, C, and D, because y is equal to a and the last person is a. So a passes it to someone other than a, and that person passes it back to a. So x has got 3 options. So x can be B, C, or D. So in this case, the number of ways that a can get back a can get the ball after n passes is equal to a n minus 2 into 3. That is 3 a n minus 2. Because the number of ways in which the ball can end up with a after n minus 2 steps is a n minus 2, and after that there are 3 possibilities for player x. So that sums up case 1. Now we come to the more interesting case, case 2, where y is not equal to a. So if y is not equal to a, then the number of ways in which the ball does not end up with a after n minus 2 passes, given that in every pass the ball goes to a different player, how much is that? That is 3 power n minus 3 minus a n minus 2. Sorry, it should be 3 power. Because for n minus 2 passes, each time the ball goes to a different player. So initially the ball is with a. In the first pass, a has 3 options to pass the ball. So that is 3. The person who gets the ball has 3 options because he cannot pass to himself. That is 3. And so on for n minus 2 passes. But notice here that the ball cannot come back to a after n minus 2 passes. So we have to subtract the number of ways in which the ball comes back to him. So after we have ensured that a does not get the ball after n minus 2 passes, we have to also ensure that a does not get the ball in the penultimate pass. So we have y, then x, then a. So y is not equal to a. It must be one of B, C, or D. So x has only 2 options now. Because a is booked, x cannot be equal to a, and x cannot be equal to y, which is one of the other 3. So x has 2 options. So the number of ways the ball can come back to A after n passes is equal to 2 times 3 power n minus 2 minus a n minus 2. So, and also we know that an, to calculate an, we have broken the problem up into these two cases. So
Okay, so Shotim, will you be going next?
No, I think Jyotishko is up next.
Okay, Jyotishko. Okay.
Can I please have some time? I mean, so I need maybe 3 minutes
Okay, yeah, sure.
for setting up my devices. I mean, yeah. Okay, so please excuse me for 3 minutes. I'll join
Sure.
from laptop. Yeah.
is my screen visible?
Yes.
Sorry, I got disconnected.
Okay.
Network issue. So we obtain this recurrence relation an is equal to an minus 2 plus 2 times 3 power n minus 2. So in order to solve this, we need some initial values. What initial values do we need? So in this case, notice that n is odd. We need to calculate the value of this recurrence for n equal to 7. So A3 would be a good initial value. So what about A3? There are 2 passes in between. So A can pass to 3 players. There are 3 choices for this place. And that person can pass to 2 players. He cannot pass to A because in that case, because the penultimate person cannot be the same as A. So there are 2 choices. So A3 must be equal to 3 into 2 equal to 6. So for any odd number, we have this. So we now can write this as a2k plus 1 minus a2k minus 1 is equal to 2 times 3 power 2k minus 1. and so on till A5 minus A3 is equal to 2 times 3. Is that right? Should be 3 power 1, right? So 3 power 3. Just a second. So notice that A1 is equal to 0. This is because in one pass, if A is passing to A, this case is not possible as we have assumed. So A1 is equal to 0. And this fits in because we have calculated that A3 is equal to 6, that is 2 into 3. So summing all these up, we get A2k plus 1 equal to 2 into 3 into 1 plus 3 squared plus 3 power 4 plus so on up till 3 power 2k minus 2. So that is a GP because it's 1 plus 9 squared plus up to 9 power k minus 1. So the sum of this GP is 9 power k minus 1 by 9 minus 1. So we get here that it's 3 by 4 into 9 power k minus 1. Now in this case we are asked to calculate A7. So 2k plus 1 is equal to 7. We obtain that k is equal to 3. So we can plug in the value 3 by 4 into 9 power 3 minus 1. So 9 power 3 is 729. And we will have here 728. Gives us 182, 546. This is the answer. But this is the general expression for an odd number of passes. So just a quick recap. We have adopted a recursive approach to solve this problem. We have assumed n to be the number of ways in which the ball can come back to A after n passes. And we have broken this up. We have broken this up into two parts. In one part, after n minus 2 passes, the ball reaches A, in which case, after the penultimate person can be chosen in 3 ways, and the number of ways in which the ball can end up with A after n minus 2 passes is an minus 2. So the number of ways in which the ball can reach A after n passes is 3 times an minus 2. On the other hand, when the ball does not reach A after n minus 2 passes, there are 2 choices for the penultimate person. And the number of ways in which the ball does not reach A after n minus 2 passes is 3 power n minus 2 minus an minus 2. So these two are multiplied, and summing the number of ways obtained in the 2 cases, we have our recurrence relation, which turns out to be this simple recurrence relation: an is equal to an minus 2 plus 2 times 3 power n minus 2. Now to solve this recursion, we need some initial values. We have calculated an for n equal to 3. where there are 3 passes played before A obtains the ball again. And we find that A3 is equal to 6, and we plug in, we sum these equations up, and finally we get the value of the number of ways. So that's all that I wanted to say. I'll stop sharing. So who is the next person? I think it's Shoutim. So he will be.
No, it's Jyotishko actually.
Oh, it's Jyotishko. So Jyotishko will be taking it from here. So
Okay. So am I audible? Am I audible? Can anyone please respond?
yeah, you are audible.
Okay. So let me share my screen and then we are good to go. Okay. So I shall be doing a problem on not exactly calculus. So I shall. Oh, I forgot to share my screen. 1 second. Yeah, here it is. Yeah, I think this is visible. Okay, so the first thing that okay, so as I was saying that previously I told that I shall be doing some problem on calculus or number theory, but I think the problem might not be on calculus exactly, so it will be on real analysis. So yeah. So the first thing that I'm going to state, I'm going to state a problem, and the problem goes like this: that suppose, just 1 second. Yeah. So we can consider this to be a problem, or maybe some result if you want. Yeah. So the problem goes like this: that suppose I'm sorry for the disturbances, this background noises and everything. Anyway, so suppose A is a sequence. So whenever we write sequence, we mean a real sequence or a sequence of real numbers. So it's a real sequence such that so the condition that is given here is this one, that is the consecutive differences, that is the difference between an plus 1 and an is strictly less than some lambda times the difference between an and an minus 1, where this quantity lambda is some number, some fixed number in between 0 and 1. Okay. So the question is it necessary that this sequence an converges? Okay. So if someone is acquainted with this concept of convergence and sequences, and so mostly Cauchy sequences, so this problem might be easier for those persons. Anyway, so this problem does not require much knowledge about this contractive about the sequences and anything. So this may come from like basics of Cauchy sequences and convergence of Cauchy sequences. So after this problem is done, so I shall be revealing the name. So what kind of sequences these? So before I start, I should tell you all that these kind of sequences has a special name. So I'll come to that later. So let's try this problem first. Okay. So yeah, so at first we can start with some arbitrary numbers, some two arbitrary numbers. Let's say m and n. Sorry. Oh, sorry. Yeah. So let's start from, let's pick up some random numbers, some two numbers, m and n. Let's pick up some, or maybe like we can say that let's pick up some two numbers. Let's say some two numbers from the sequence, from the sequence an. Let's say am and an. So whenever I am writing these kind of thing, so it means a sequence, and so when I write an, just simply an, so it means the nth element of this sequence, or the nth number in the sequence. So yeah, so this is the scenario, and so now let us try to find out. So can we bound this difference? Can we bound this difference by some way? Okay. So since if one has proceeded up to this, the most natural thing that one might be thinking about is, so since in the problem we have something like this, just can you please wait for 1 second? Yeah. So so just asking, is my screen visible and everything's fine? Can anyone respond? Shotim, can you please respond?
Yes, I can hear you.
Okay, all right. I mean, yeah. So one natural approach that one might be thinking of, if someone has proceeded up to this, is that since we have some kind of consecutive differences in the problem statement itself, so we can try to write this thing. We can try to write this difference between am and an in this manner, right? Like this. So okay, so one assumption here is that this m is greater than n, of course. So we can try to write this thing like this. That's a quite
yeah, I can hear you perfectly, but actually last few seconds are a bit fluctuating. Now it's okay.
Okay. Now it's fine, right? Oh, okay. Yeah. So what I was saying is that we are simply writing this difference between am and n in this manner. So I mean, the intuition behind this kind of approach is from the problem statement itself. So the problem statement says what? It deals with some kind of consecutive differences. That is, the consecutive differences between the differences between consecutive numbers in the sequence. So we can simply write like this. So we are writing this difference n minus an as am minus 1 plus am minus 1 minus n minus 2 plus am minus 2 and so on. So we shall end at here, right? Sorry. So this is the place where we shall end. Now, this is quite apparent from here. We might be. Shotim, can you please? Yeah. Thank you. Okay. So yeah, so we can use the generalized triangle inequality. I don't know if that's a valid term or not. Anyway, so we shall be using the simply using the triangle inequality. So which is basically this. So if we have a1, a2, and so on, and let's not use a1, a2. Let's use something else like lambda 1. Oh no, lambda, no, not lambda. I mean maybe b1, b2 up to, let's say, bk. This is less than or equal to mod of b1 plus mod of b2 and so on. So this is a quite famous identity or famous result, as we all know. So okay, so if we use this result here, so what shall we get? We shall get this one, that is am minus 1 plus. So these consecutive differences will turn up here, right? So now, since we have something familiar in our hand, we can use these things in some way, right? All right. So now let us come back to this problem statement once again. So in the problem we have this n plus 1 minus an. This is less than lambda times an minus 1. Again, this is true for, since so I did not mention it here, but this is quite obvious that this result, or I should say this given statement holds for all the natural numbers n. So now this holds for this thing too, right? Okay, let me scroll up a little bit. Yeah. So this identity, this result holds for this thing also, right? Therefore, we can write this as this is less than or equal to lambda times a n minus 1 minus a n minus 2. So instead of writing this lambda twice, let me just simply write it as lambda squared times, let me move this thing a little bit left. Yeah. So in the similar, in an exactly similar manner, we can proceed like this. So this will be less than or less than lambda cube times a n minus what? N minus 2 minus a n minus 3 and so on. Right. So where should we stop? Obviously we shall stop when we shall hit this last consecutive difference, that is this a2 minus a1. Right. All right. So now from this pattern one can easily observe that. So 2 and this power was 3. So the sum was n minus 2 plus 3, that is n plus 1. And one can check that this is true for if we, I mean, all of these steps. So obviously if this last step, this we should have. So the question is, what is the power that should go here? So it should be the sum of these two and these things should be n plus 1. So it should be n minus 1, of course. Okay. And remember that this is true for all natural numbers n. Therefore, okay, so let me move this to some other place. Okay, no, it's not necessary. So from this step onwards, let me mark this as a star. So let's continue from this star again. So from star, what can we say? We can say that the difference between am and an will be less than or equal to. So from this first term, what do we get? We get the difference between a2 and a1 times lambda power. It should be lambda power. So for n plus 1, it was n minus 1. So for m, it should be what? It should be m minus 1, right? Oh no, it should be n minus 2, I guess. Yeah, it should be n minus 2. Yeah. So coming back to this again. So it should, this is less than or equal to, let me write this once again. This is less than or equal to am minus 1 plus am minus 1 minus am minus 2 and so on up to I guess an plus 1 minus an. Yeah. So now by this result that we have proved just now, so this first term is less than what? This is less than lambda power m minus 2 times a2 minus a1. The second term, the next term is of course less than this was m minus 2 here, so this should be m minus 3 and so on. So the last term here, that should be lambda power. So this is the exact case that we solved. So it should be lambda power n minus 1 times a2 minus a1. This difference, right? So now what we can do is that's quite apparent from here. That is, we can take out this lambda power n minus 1 as the common term, and of course this a2 minus a1. So in that case, what shall we get? We shall get this 1 plus lambda square up to. So I'm just writing everything in the reverse direction. That's quite understandable, I guess. Anyway, so it should be something like m minus 2 minus n minus 1. I mean, I should say n plus 1. So it should be m minus n minus 1. Yeah. All right. So now one thing that one should notice here is that this lambda is a number, is a fixed number in between 0 and 1. Therefore, this series 1 plus lambda square up to infinity, this is summable, and the sum is, this infinite sum is precisely 1 by 1 minus lambda. Therefore, and since this lambda is positive, so can we write this? Can we write? Okay, so yeah, it's fine. So can we write this, that this is strictly less than lambda power n minus 1 times the difference between a2 and a1 times this infinite sum. So I'm simply extending this. So this series ended at the m minus nth position. So I'm simply extending it up to infinity. Okay. So what we get here is
this is equal to, this is precisely equal to lambda power n minus 1 divided by, this should be what, 1 minus lambda times a2 minus a1. Right. Yeah, all right. So let me see, since lambda is a fixed constant again, so we can simply multiply this, both the numerator and the denominator, by lambda, and that will give us lambda power n. I mean, it's not necessary, but I mean, this is just for convenience, for notational convenience. So so we can write like this, I guess, that is a2 minus a1 divided by lambda times lambda 1 minus lambda. Yeah, and remember that since lambda is a constant, so this denominator is a constant, and since this a2 a1, so an is a given sequence, so a2 and a1 are given things, given numbers. Therefore, this whole thing that we have here, this is a constant. So remember that this thing is a constant. So let's call this C. Therefore, we can write this as some constant C times lambda power n. So where did we start from? We started from the difference am minus an, where am and an are two arbitrary terms of the sequence, where am is greater than n, right? And now we have come to this. We have found out that this difference am minus an is strictly less than. Remember that we have two strict inequalities here. So therefore, this difference is strictly less than some constant c times lambda power n. Okay. All right. Now one can approach this problem in two different ways. So basically, yeah. So so now we can consider as n goes to infinity. Now what we can do is we can send this n to infinity, or I should say tend, not send. Okay, so we can tend this n to infinity. And so there might be, so we might give an epsilon delta argument, but that might be difficult for some people, I mean, who are not quite familiar with these epsilon delta notations and these definitions of convergent sequences. And I mean, these epsilon delta definitions might be a little bit confusing at times. So let us not go into that. So I mean, so what I want to say is that, so basically for any given epsilon, so remember that this lambda is some number which strictly lies between 0 and 1. Therefore, of course, we have this, right? Lambda is greater than lambda square, greater than lambda cube, and so on. And remember that this limit, I mean, as n tends to infinity, this thing, lambda power n, this goes to 0, right? Since, I mean, this holds only, I mean, if and only if this lambda lies between 0 and 1. I mean, that's quite easy. Anyway, so now what we can do is for any given epsilon positive, epsilon is, so you can, so for those who do not know about this epsilon delta definitions or anything, so one can assume this epsilon to be any constant, any fixed constant, positive constant, of course. It might be small, it might be large, it doesn't matter. So it should be in any fixed number. I should say any given, yeah, it's fine. Any fixed epsilon positive. Any fixed epsilon positive, we can say that there exists some natural number, let's say in epsilon, such that what happens? Such that this lambda power, so I should write that such that for all n greater than or equal to n epsilon, we shall have what? We shall have this quantity, this c times lambda power n will eventually be small. Okay. So let's work with this. So since the c is a constant, that does not bother us much. So we can work with this lambda power n only. So we shall have, so for all n greater than or equal to this n epsilon, we shall have this lambda power n term will be strictly less than epsilon by c. So where c is this constant. Okay. So yeah, I mean, this is quite intuitive, quite intuitive because see, suppose let's consider this here. So let's say 0, 1. So now let's say you have chosen. So if you have chosen this epsilon to be something large, in that, I mean, if this epsilon by c is something which is greater than 1, in that case any I mean for any natural number n, lambda power n will be less than epsilon by c. Now what if this epsilon by c is some small number which is quite close to 0? Let's say epsilon by c is somewhere here. Now since this lambda power n will eventually tend to 0 as n goes to infinity, therefore after some number, so let's say our initially our lambda was here. Since we know that lambda, so this sequence lambda power n is a strictly decreasing sequence, what we shall have is this thing. So if lambda is here, so lambda square might be somewhere here, lambda cube might be somewhere here, and so on. Now obviously it's not epsilon by n, it's epsilon by c anyway. So eventually what will happen is we shall cross this epsilon by c sometime, because otherwise we shall never be able to reach this number 0, right? Now okay, so now this is, so I'm not arguing rigorously here. So now, but I mean, this can be formalized very easily. Anyway, so let's not go into that much of rigor. Yeah, so basically this is what I wanted to say. And finally, so once we have said this, so it means what? It means that for all natural numbers n greater than or equal to this n epsilon, we shall have c times lambda power n. This will be less than this epsilon. And remember that this holds for every single epsilon positive. So there are uncountably many epsilons, of course. So, and for each of these epsilons, for any epsilon positive, any fixed epsilon positive, this result holds. So this cutoff in epsilon, this is of course dependent on epsilon, but still this holds for every single epsilon. Therefore, what we can say is that, and it implies that for any fixed epsilon positive, there exists some natural number in epsilon such that for all natural numbers n greater than or equal to this n epsilon, we shall have this and then this. And since we have shown that the c times lambda power n dominates this number a minus n, I should not use the term dominates because that might mean something different anyway. So this thing is upper bounded by c times lambda power n. So therefore, this inequality holds. And again, let me repeat this once again, that this holds for every single epsilon positive. This directly implies that. So now this might require some knowledge of Cauchy sequences. I mean, this is, so for those who do not know, this is the exact way, I mean, this is the precise way how Cauchy sequences are defined. So this means that the sequence n is Cauchy. And so again, so this is something that all people might not know, that every single Cauchy sequence in R is convergent. So since this is Cauchy, so we can simply write here that hence convergent. Okay, and so we are done with this problem. And so I mean, so some of you might have forgotten the problem statement itself. So it was that, so if this holds, so let me write here that if this holds for a sequence, for this sequence an, and if it holds for all natural numbers n, in that case, the question was, is it necessary that this sequence an converges? The answer is, as we can all see, the answer is yes. It should be convergent. I mean, it must be convergent, I should say. Okay, so from here we might be, I mean, so okay. Now, as I promised that I shall tell you all that these sequences, these kind of sequences, let me go back there. These kind of sequences has a special name. So we call it contractive sequence. Okay. So the result that I have essentially proved here is that any contractive sequence is Cauchy and hence convergent. Okay. So yeah. So so this is something that you might find in some analysis books. Anyway, so now using this, we might try to solve a problem. Okay. So problems are interesting, always interesting. So let's try one. Okay. All right. So let's try a problem. What happened? Oh yeah. Yeah. So let's try a problem now. Okay. So the statement of the problem is quite simple. It says what? It says that suppose f is a function. So when we mean that f is a function, it by default we have to assume that f is a function from R to R, at least at this stage. Is a function, or maybe let me write that f is a function from R to R, satisfying this inequality, that is fx minus fy, the difference of that, absolute difference of that, is less than or equal to half times this, and this holds for all x and y in R. So now what we are supposed to prove in this problem, prove that there exists exactly one fixed point. Okay. So again, for those who do not know what a fixed point is, so fixed point is nothing but, so if we have a function f, so a fixed point of f is a point c such that fc is equal to c. So in general, so the set of all fixed point of a function f is the set of all points x such that, okay, so let me write here. So this fixed point, this term fixed point, this refers to, let's call that maybe f, or maybe p. So if so this is the set of all fixed points. So and what does it say? It means that all x such that fx is equal to x. That the definition is quite simple. So now what you need to prove is that in this problem is that this function f, which I mean a function, if a function f satisfies this condition, this difference between fx and fy is less than or equal to half times the difference between x and y for all x and y in R. In that case, these kind of functions has exactly one fixed point, not zero, not more than one, but exactly one fixed point. Okay. All right. So now this is so once we have done the first one, now this might, this might ring a bell that yeah, so the result of this contractive sequences are Cauchy. This might be helpful in some way. Okay, it may not be, but so since the pattern is somewhat like this, right? So let's try in some way. Okay, so the first thing in this kind of problems is one might be showing is that, so look at this problem statement once again. So what you need to prove is that there exists exactly one fixed point, right? So if you have, okay, so as I said, exactly one means not zero, not more than one. It should be exactly one. So what does it mean? So it means that we need to prove that. So we might be interested in proving that there cannot exist two fixed points, let's say P and Q at a time, right? Okay, so let's start with this. That suppose this function f has two fixed points, or maybe more than one, I should say, has more than one fixed points. Let's say what? Let's say P and Q. And of course, P is not equal to Q. Okay, so in that case, what will be, okay, yeah. So that is, so this means what? So since these are fixed points, therefore, fp is equal to p and fq is equal to q. Now, if we have this, then let's plug these p and q in our given equation. Not equation, the inequality. So it means what? It means, so since fp is equal to p and fq is equal to q, therefore we can write this. So this is less than or equal to half times p minus q by the problem statement. And of course, this is a contradiction because we all know that. So since this is a positive quantity, therefore this is strictly less than mod of p minus q. Since p and q are, so I'm using the strict inequality here. Since this p and q are assumed to be, by default, assumed to be different. Okay, so this is a contradiction. So this is a contradiction that we have got here. So it means what? It means that these first assumption, that is f has more than one fixed point, this is not possible. Therefore, the maximum number of fixed points that this function f can have is 1. It might have no fixed point at all. I mean, as of now. So we need to prove that there exists a fixed point for sure. But I mean, right now, as much as we have proceeded, it's not apparent that it might have exactly one fixed point. It might happen, right, that it may not have any fixed point at all. Okay, so let's try to do that. So let's try to find out a fixed point directly. Okay, so in that, for doing that, we might do one thing. So again, so this is quite intuitive. Once you have done this first problem, this one. Okay. So again, so since this is similar to the, so we can relate this problem statement. So we can relate these two problem statements for this question, this second problem, and this first problem of contractive sequences. Okay. So why not? We can do this. That, so let us define some sequence. Let's define, let's say, define some sequence. Let's say, maybe let me write this, define a sequence. Let's say an once again, or maybe let me use something. Oh yeah, it's fine, an. Such that, let's say a1 is equal to 1. Okay, and f of an, we shall be defining it as an plus 1. Or maybe I should write the other way around, that is an plus 1 should be defined as f of an. Let's do that. So now, the nice thing about this, so once we have defined a sequence like this, the nice thing that we have here is that, so the problem statement that we have, this gets converted into what? Once again, yeah. So this gets converted into, thus we have the difference between, let's say, okay. So now let us put x is equal to an and y is equal to an minus 1. Okay. If we do that, what do we get? We get, if we put x is equal to an and y is equal to an minus 1, then what shall we get? We shall get f of an minus f of n minus 1. This will be less than or equal to half times this difference. Right? Now, as per our definition, as far as we have defined, so this is equal to an plus 1 and this is equal to an. So essentially we get this thing. This implies what? This implies that an is a contractive sequence. So again, so if someone has forgotten what this contractive sequence means, so okay, so let me write it right here, that these kind of sequences are called contractive sequences. I have mentioned it earlier, but anyway, so people are forgetful anyway. So So these sequences are called contractive sequences. And as we have proved, let me repeat once again that contractive sequences are Cauchy, as we have proved, and hence convergent. Okay. So now, since we have proved that say n is a contractive sequence, it means that n is convergent, or maybe let me write n converges. So what do we mean by n converges? That is, this limit exists, right? So limit n as n tends to infinity is some number, maybe let's say something, maybe I don't know, let's say c, or maybe l. So suppose not suppose, I mean since it n converges, so let's say to l, that is limit of the sequence an as n goes to infinity. This is L. Now, all right. One second. Yeah. So, yeah. So, as per our definition, as we have, so we have defined what? We have defined this, I mean, we have just defined this n plus 1 to be fan, right? So now, since this sequence, we have proved that the sequence an converges, we can take limits on both sides. So it means that this is the case that we have here. Okay. Now, since we have just assumed that limit of n as n goes to infinity is L. Now, okay, so yeah, so let me write this once again. Okay, so now one question that might be arising here is that can we take this limit? Can we take this if outside of the limit? That is, can we write this? Can we write this? The answer is yes, because this function f has to be continuous. Okay, so now this is another concept of continuity. This comes in picture. Anyway, so I guess this is understandable from this first statement itself, because I mean it follows directly from this first statement actually. Okay, so again, so if one has studied about these epsilon delta definitions, so I guess that's quite obvious from here. Anyway, sorry. Yeah. So therefore we can, so now we know that for continuous functions we can do this. So for continuous functions we can do this kind of operation, and since we can prove that if this function f is continuous, that's quite, I mean, that's a simple proof. So therefore we can write this, and once we have written this, as we have stated earlier, that we have assumed this limit of an to be L, right? And so we have directly found out a fixed point of the function f. Now, as we have proved earlier that f cannot have more than one fixed point, and now we have already found out one fixed point. And what does it mean? It means that L has to be the only fixed point of this function f, right? Yeah. So that's what this problem says. Okay, so let me write here. This fixed point is the only fixed point of f, since we have proved that . if cannot have more than one fixed point. Yeah. So that proves our problem statement that we wanted to show. Yeah. So this is all that I had to say. So yeah, thank you. Hello. So am I audible? Hello.
Yes, you are audible. Can you just wait for 2 minutes? I'm trying to join from my laptop.
All right. So let me make you the host, Shoti.
Not right now. After I join from my laptop.
Yeah. I'm sorry. Yeah. That's fine. Okay.
Okay, so Shotim, are you next?
Yes, I just need 2 minutes to
Okay. So let me make you host.
configure my devices.
Yeah, Jyotishko, can you make Shotim host?
Hello, am I audible?
Yes, yes, yes. Yeah, Shotim, you are now the
Okay.
host.
I'm sorry, I had to receive a call. So, I mean, did I miss something?
Hello.
Yeah. So,
Am I
did I
audible?
miss something? I mean,
No,
you had to
you did
receive a
not
call.
miss anything. I'm almost ready to start.
Okay.
So can you make this? Can you make me host?
I mean, I can see that you are the host. I don't know.
Okay. Orkuda has made me the host already.
Okay.
All right. Thank you. Yes. So I've started sharing my screen. Is it visible?
Yes, it is.
It is visible, right?
Yeah.
Okay. So yes. So essentially, for this workshop, so I'm going to teach you algebra in the workshop. All right. But actually, the thing that was missing in this demo workshop is geometry. So no one has talked about geometry yet, and I feel that such a workshop that is focusing on ISI and CMI is incomplete without having a geometry problem in it, right? Because uh, it's like uh, a probability one event that you'll get a geometry question paper in the part B of ISI, and likewise in CMI. So, anyways, so before I start, I would like to say that there are two approaches to solving a geometry problem. At least there are two approaches that I have often experienced during my problem solving. That one is the harder approach, which is often called bashing, and the other is often the more difficult to see, difficult to perceive, and all that kind of an approach. So that is the elegant approach using angle chasing, looking for similar triangles and cyclic quadrilaterals, and so on. So today, essentially, I will give you all a problem. That problem will be that problem can essentially be solved in two ways. Okay. So as I said, that it can be solved using bashing, and also it can be solved using uh, like Euclidean geometry observations from your high school days. Okay, so nothing fancy. Okay, so anyway, so here it goes. So the problem is uh, so I have a triangle ABC. Okay, and it's given that angle B is 40 degrees, so is angle C. So essentially this is an isosceles triangle. Okay, and also and the problem has also provided that this line segment that I'm drawing is the angle bisector of B. So what do I have here? I have 20 degrees here, I have 20 degrees here. All right, and let me name this point. So let me call this point D, say. Okay, all right. So what the problem? So it's as simple as this. So nothing too complex. And what you are essentially required to show is that BD plus AD is equal to BC.
Shrutim? Hello? Hello? Hello?
Yeah, you're audible. I think Shrutinda didn't unmute.
Yeah, Shrutim, hello? Hello? Shrutim, can you... Uh, okay, let's text Shrutim. Hello?
Yeah, you're audible. I think Shrutinda didn't. Hello?
Yeah, Shrutim, hello? Yeah, Shrutim, you're not audible.
Okay, since when my
Yeah, now you're audible.
I mean, since when was I got it?
I think from the beginning.
Sorry, I'm what is the again?
Yeah, Shrutim, you're not
Just
audible.
speak some.
Yeah, now you're audible. Yeah, Shrutim, you are the host now. So,
Yes, I'm trying to.
you have to share your screen. Your screen.
Yeah, I'm trying to join from the internet.
Okay.
Actually, I'm at the hostel and the internet connection is fluctuating. And also, probably take over and
Are you telling me to take over the meeting?
yes, because see, we cannot speak and we cannot speak and share from the same device.
Okay, sure.
Please take over.
Yeah, sure.
Anyway, there's a lot of discussion.
Yeah,
Sure.
so yeah, Shrutim's audio is also not working clear. So yeah, Orcosina. So then I'll be okay. Shrutim, can you make Orcosina a host?
Yes.
Yeah, Orcosina, you are now the host. So
Okay.
you can share your screen and go ahead.
Sure. Okay, so let us start with a problem that came in 2019 as an entrance examination. So am I audible, guys?
Yes, you are.
Hello? So let us begin with this problem. We are told that 1 by 2y times x minus y dt is equals to f of x, where and y is greater than 0. Okay, so first of all, see that this equation involves an integral and two variables. That makes it look kind of spooky, but there's something else given as well. Okay, so what's the something else? It's given that f is twice differentiable. And we are required to show for some a comma b belonging to real. So what the problem essentially tells us is that we need to show that a function that follows this criteria for all x belonging to real and y greater than 0, the function itself must be linear. So, and we are given that the function is twice differentiable. So let us start with the solution. So see, intuitively, if you see, what does this mean? Sort of means like the area between, so let us start with the diagram. Rather, let us just first differentiate it, okay, with respect to, so first of all, see, this looks a bit messy. So why not just put the 2y this side and make it a bit more aesthetic. Okay. So now what we do is that we differentiate this with respect to y and see what happens. That 2 times f of x note that there is a plus sign here. Why should that be? Because there's this minus sign here in x minus y. So when you take the derivative, due to the chain rule, the minus 1 comes as well, and you get this. See, this equation, if you think about it, gives you a strong sense that f should be linear, right? Because what are you doing? You're calculating, say this is x. You're going a little back and a little bit front. You're seeing the values, taking the average, and that is the value of the function at x, right? So, and this is true for every x and every y positive. So what you're doing is basically you're taking any point x, you're going a little bit back, a little bit front, averaging the values, and you're getting back the value of the function at x. So this like gives you the intuition that yeah, this should be linear, right? Because if it had been a curve like this, then what would have happened? The average value is either above or the average value is below. Okay. It may happen that for some cases, for some unique cases, this condition holds, but this holds for every x and y positive, gives you a strong sense that yeah, this function should be linear, right? So what do we do then? We're given that this function is twice differentiable. Okay. So what can we do? Let us take the derivative of this function with respect to y. So this does not really involve any y. So f prime of x plus y minus f prime of x minus y gives you 0. Okay, nice. Well, we have come a long way because we started out with something like this, rather this, and now we have something that looks quite more friendly. Okay. So before I proceed further, the question tells you that the function is twice differentiable. But as it turned out, we can actually do it even less. And that we shall see when we proceed. Okay, so let's just do that. You see, f prime of x plus y is equals to f prime of x minus y. X belongs to real, y greater than 0. So take two cases. X is greater than 0. Then you can just take y equal to x, and then what do you get? F prime of 2x is equals to f prime of 0. Okay, for all x belonging to r plus. Okay, this basically means that f prime of x is equals to f prime of 0. Rather, don't take this as x, take this as some t, where t is equals to 2x. So basically, what does this mean? For any positive value of t, the derivative of f with respect to t is a constant. Okay, so one very important and very intuitive fact about linear functions is that their derivative is constant. So half the thing has already been done. Okay, so what we showed that for positive, its derivative is a constant. F prime 0 is a constant, right? Now we look at the case 2. X is less than 0. Then just take y is equals to minus x. And what do you get? F prime of 0. F prime of 0 is equals to f prime of 2x. Once again, which we can just restate as f prime of t is equals to f prime of 0 for all t, for all x belonging to minus. Okay, so what did we get? We get that f prime of t is equals to 0 for all x belonging to r. Okay, but we have been given that f is twice differentiable. Just a few minutes back, I told that we can do with much less. We can just assume continuity of the first derivative. We can just assume that if f prime is continuous, you should remember this, that differentiability implies continuity, not the other way around. So continuity is a weaker condition than differentiability. So if we just assume that the first derivative is differentiable rather than assuming that it's differentiable, we can claim that since f prime of t is 0 for all real numbers that are not 0, and we can just take t tends to 0 and claim since it's continuous. So just consider this, f prime of t limit t tends to 0. What is this? This is equals to 0 because at every value of t not equal to 0, this thing is 0. But since this is continuous, this is just f prime of 0. So what did we get? We get that f prime of x is some constant. And what does that mean? That simply means that f is a linear function. You can just integrate this, okay, and that is pretty apparent. So what did we do? Let's just sum up the ideas. We saw something that looked pretty ugly. So we made it a little more beautiful. And since we don't like integrals in our equations, so we differentiated it. First with respect to y, and then what did we get? We got this, right? From this, what did we see? We saw that this equation gives us a strong feel for linearity. So our belief in the question grew stronger, and that gave us a bit more confidence because this condition intuitively tells you that, yeah, this must be differentiable. So you get confidence in moving further, and that's something very important in the examination hall. So what did we do next then? We differentiated it again, this time with respect to y once more, and we got something like this. Then what was the motivation behind taking y equal to x? So that I can just get a 0 here. See, I don't like many variables in my equation. I want as many less variables that I can get, and at the least number of places. Okay. And why did we have to put the condition of x greater than 0 and x less than 0? Because y had a condition on it that y had to be greater than 0. Okay. So since y has to be greater than 0, so we take two conditions and we see that there are two cases, and in both the cases the value of the derivative of f comes out to be constant, and the only case that was remaining was that of t equal to 0, and that we argued by continuity that it had to be nothing less than f prime of 0. So what we got that f prime of x is a constant, and that is equivalent to saying that f is a linear function, and thus we just proved what we were asked to. So that's it for this problem. Next, we try another problem. Okay. Let's go to problem number 2. We are given that if 1 to 2 are continuous. Okay. Well, that's a pretty bad spelling mistake. Okay. And we are given that f of x is equals to and we are asked to prove that okay. So we are given that f is a continuous function from 1 to 2, two real numbers, and it's continuous. And we are given an expression for f of x that doesn't really look nice, but what can we say? We have what we have. So, and we are asked to prove that f is a constant function. See, when you're given continuous functions, one very important thing is to look for what is the interval in which we are asked the question. See, a very important property of continuous functions is this. Let me just change the color. Yeah. See, a continuous function in a closed bounded interval has a maximum value and a minimum value, both of which it attains. F continuous in a closed bounded interval, F will attain maximum and minimum value. Okay. Okay. So let us keep that in mind and proceed. Okay. So let f attain the maximum at x naught, and let f of x naught be what? Let it be b. Okay. Or rather, let it be big M. Okay. So of x naught is equals to summation of to the power 1 by n by 2 to the power n. Okay. Now, what can we do? So this is maximum. And since each value of this thing, f of x naught whole to the power f of x naught to the power 1 by n, this must be less than equal to m, since at x naught we get the maximum value. So f of x naught to the power 1 by n has to be less than equal to m always. Okay. What does that mean? That means if you take this sum, okay, if you take this sum, this has to be less than equal to b to the power 2n sum. But what is this sum? This sum is equals to b, right? Simple geometric series. Okay, so everybody knows the formula of the sum. So this sum is just b. So if any of these f x naught to the power 1 by n, okay, I think I messed up my notations. This be m. This was m, right? Yeah. I took b for the upper bound. Well, just bound came in my mind and I just put it b there. Anyways, so let's just go back and get a recap. So the important property that we're using here is that in a closed bounded interval, every continuous function attains a maximum and a minimum. What did we assume? We assume that if the maximum value of f is at x naught, where obviously x naught belongs to 1, 2, and it has some maximum value, we call it m. We look at this, the definition of f of x, okay, and see that this, the left hand side is m. We come to the right hand side and look at these things. Each of these is less than equal to m, since x naught is the value at which f attains the maximum. Okay. So f of x naught whole to the power 1 by n will obviously be less than equal to m. Now we look at this sum. So this sum must be less than equals to this thing. This sum must be less than equal to this thing, but this is equal to m. But we know that the LHS, this thing is equal to the LHS, right? So this thing must be equal to m. What does that mean? That means that each of f of x naught to the power 1 by n had to be equal to m, right? Since this sum is less than equals to m to the power 2n, sorry, less than equal to m, and we already know that from this line that this sum has to be equal to m. That means each term of this sum, rather the numerator of each term of this sum, has to be equal to m, because if any one of them had been less than m, the whole sum would have been strictly less than m. Okay, so we get this for all n. Similarly, if you look at the minimum value, let f attain its minimum at x1. x1 be L, or rather just use small m. Okay. So in that case, what will it be? We'll get that f of x1 is equals to summation of f of x1 whole to the power 1 by n by 2 to the power n. Since x1 is the point at which f attains its minimum value, and mind you, the minimums we are talking here are not the like local minimum or local maximum. They are the global maximum and global minimum. This theorem tells you about the global condition. Okay. So this sum, rather this sum, this sum is equals to what? This is equal to m, and I know that f of x to the power 1 by n is less than equal to m, from which this follows. So if you take the sum from n equal to 1 to infinity, this sum has to be less than equal to m, but we know that this sum equals m. So f of x1 to the power 1 by n has to be equal to m for all values of n, because otherwise this sum would be strictly greater than small m. But wait a second, we got that f of x, let's just write in the next page, we got that f of x1 to the power 1 by n is equals to small m, and f of x0 to the power 1 by n is equal to capital M for all n belonging to natural numbers. What happens if we tend n to infinity? See, x1 and x0 belong to what? 1 to 2, right? So x1 or x0 to the power 1 by n would tend to what? 1, right? And since the functions are continuous, the function is continuous, so which is equals to f of 1. Similarly, we get what does that give? That give me m is equals to m. That is, the minimum is equals to the maximum. And that just simply means that the function is a constant, because had it not been a constant, there have been distinct maximum and minimum. So we are done. Okay, guys, so that was my part for the demo class today. So I would request Orkoda to take over. Orkoda, are you there?
Yeah, actually, I can take over from here. Thank you, Orko.
Okay.
Yeah. So I hope there are no audio video problems right now. Orko, if you can stay here for, I'll not take long. So if you can stay here for 10 more minutes, maybe, to check whether there is any audio problem during the meeting.
Yeah, Orko, hello.
Yeah, sure.
Are you there?
Yeah.
So yeah, someone has asked a question, Tomojit Shorkar. Do we have to use integration as limit of sum in this problem? So
I think no. The way I did it didn't really require that.
okay.
We just took derivatives.
Okay, thanks a lot. So yeah, Shruti, we can continue.
Yes. So my screen is visible now and I'm audible, right? Can someone confirm that?
Yes, it's working.
Okay. All right. So essentially, I my audio got disconnected in the middle of the problem while I was taking the problem. So I'll restate the problem for you. Okay. So I have a triangle. I have a triangle ABC. All right. And it is given that this angle and this angle are equal and both have measure 40 degrees. Okay. All right. So, and it is also given that this BD line is the angle bisector of angle ABC. Okay. So we are supposed to prove this BD plus AD equal to BC. So initially these were not given. So these were obtained by very simple angle chasing. So I just want to impress upon you that the geometry of this problem is as simple as this, that there is just a triangle, an isosceles triangle and an angle bisector. Okay, so maybe that could motivate you to take a bashing approach, or maybe it depends from person to person who would prefer what. But I would say that I would tell you both the approaches. All right. So the first thing that we can do in Olympiad geometry terms, it's called trig bashing. So it's nothing fancy. It's just bashing using trigonometry. Okay. So you see that. Let us write down the angles that I just erased. Let me just put them. Okay, I can just maybe undo them. Yeah. So all right. Now, see, if I have a triangle with so many angles depicted, the first thing that comes to mind if I am using trigonometry is the sine rule, right? So essentially, what we want to do is we want to express BD, AD, BC in terms of some common entity. Okay, so let us try and figure out what that common entity would be. Okay, I mean, by entity, I mean that we want to establish a relationship of BD, AD, and BC with some side of this triangle. So what do we essentially have to do? We have to look for a side that is present in at least one of the triangles with BD, AD, and BC. Okay. Anyway, so lots of triangles. Where to start? I have ABD and BDC. So notice that BD and AD are in triangle ABD, so that might be a good place to start. So applying sine rule on triangle ABD, we obtain BD by sine 100. Look at the figure. Maybe rotate this. Yeah. So from the figure, it is clear that BD by sine 100 is equal to AB by sine 60. AD by sine 20 is equal to AB by sine 60. So that's more or less all the information that we can capture from triangle ABD. Okay, so what am I left with? So what essentially, see what I have done. I have established a relation or an equation that links BD and AD to AB. Okay, so if I am able to link BC to AB as well, then I'll be able to make some progress, possibly. So if what can I do? I can essentially look at the biggest triangle of all. See, I can look at this triangle, and if I do look at this triangle, what I'll find is that, if I apply sine rule on this triangle, what I'll find is that BC by sine 100 is equal to AB by sine 40. Okay. Notice that applying sine rule on BDC is of no use because it does not involve AB in it. Okay. So, all right. So let me just I have just written down this because I will possibly be needing it later. So now, what is BD plus AD then? BD plus AD is then taking AB by sine 60 common. It's just sine 100 plus sine 20. Okay. And I know that sine A plus sine B is nothing but 2 sine A plus B by 2 cos of A minus B by 2. All right. So if with that in mind, I write this down at 2 sine 60 cos 40. Okay. And sine 60 gets cancelled. I'm left with 2AB cos 40, which is same as sine of 90 minus 40, which is sine 50. Okay. So once I have arrived here, take a close look. Okay. So my aim is to reach to this. Okay. I have to show that 2AB sine 50 is equal to BC. So what can I do? I can clearly see that there is a sine 100 in this expression, right? So if I am able to introduce that sine 100 somehow here, then I'm done. I'll possibly be done, I should say. So that gives us a clear indication. And see, there is 2 sine 50. So it is asking you to be completed, this expression. Okay. So all you have to do is multiply cos 50 in the numerator and denominator. So that makes the numerator sine 100 and the denominator sine 40. Okay. Cos 50 is just sine 40. Okay. And essentially we have the expression for BC. Okay. So very simple problem, very simple solution, yet I would like to stress that these kind of, these kind of trick bashing methods won't be so easy to, you can obviously, but due to time constraints and computational skills and all that, trick bashing and complex bashing and such kind of bashing techniques are often like not recommended. Okay, so but what I would say is that if you cannot attempt your if you, see, the time constant is very real. Okay, so you have to manage your time very efficiently. So I'm saying go for this approach. Do not refrain from it. If you can proceed using, say, at least you can establish, if you can make some definite amount of progress in the problem using this kind of bashing, then you obviously merit some points. Okay, it's better than not writing anything at all, not providing any idea at all. And in some of the cases, or if you are clever enough, if you can bash well enough, then you can come up with the correct solution often. Okay, so anyway, so the second method uses nothing but arguments from Euclidean geometry. Okay, so I have to write this down, just a second. So this is method, I used a green pen then. So method 2. So this is Euclidean geometry. Okay, so once again, I have the same problem. Let me just copy paste this figure. That will be efficient. Yes. Okay. All right. So for tackling geometry problems using, so what options you have here? You have all the fundamental tools at your disposal. What are they? So you have things like similarity, congruence, and cyclic quadrilaterals, angle chasing, and such things. Okay. So this problem is some good old angle chasing and some cyclic quadrilaterals. Okay, so the cyclic quadrilateral argument is very, nice here. So okay, let's do something. So our objective is the same. Our objective is to show that BD plus AD is equal to BC, right? Let us. Okay, so one more point. Let me write this as 0.0. You might be needing it sometimes and you might not, which is construction, obviously. Okay, so in this problem, we'll be mostly requiring 0, 2, and 3. Okay, so the construction is essentially very nice. So what we do is we do this. Strange, right? So why have I done this? So I'm trying to introduce some additional information. I'm looking at, from this geometric structure, what additional information can I derive, right? So in that quest, the first step that I take is take a point on this line BC. Okay, call it maybe, I don't know, say E. Okay. If I can make this triangle isosceles somehow, if I can choose this point E in such a manner such that this triangle BDE is isosceles, then I'll have a lot of help. Do you see that? So because this BD and D will then be equal, BD and BE will then be equal. And all I will have to show in that case is that AD equal to EC to get my result. Okay, So that is a motivation for such kind of a construction. So I'll write it down. So step 1, okay. Step 1 is construction. So the construction is essentially choose E on BC such that BD is equal to BE. Okay. All right. So now can someone tell me what is, you can comment if you want to. What is the measure of this angle? So this is an isosceles triangle. So the fun thing that came out of this is I have some additional information, right? So I have this isosceles triangle. So this introducing this construction gives us some additional information which helps us solve the older problem. Okay, so that is the motivation behind construction. Okay, so now yes, so what is this angle? This angle is just 80 degrees, right? Why? Because that is just 180 minus 60 whole divided by 2. All right, okay, fine. So now what is this angle then? Notice that this angle is also 40 degrees. So I have, this is very problem specific, but see how this construction gives me, I can conjure 2 isosceles triangles out of nowhere, it seems, using this construction. Okay, so I have an isosceles triangle here, which shows that DE is equal to EC. So I'll write down. So observe, so step 2 is observe. So step 2 is essentially an angle chase step. So this angle chasing step essentially tells you to observe that triangle EDC is isosceles. Okay, I should write this as an observation. Observe that triangle EDC is isosceles, implying ED is equal to EC. Okay. All right. So now what do we do? So again, what do we need? What do I need? So what I essentially need is, so I need essentially EC. Yeah, I have BD. Okay, so I'm sorry. I'm sorry, there is an interruption. Okay. Yeah, so we are back. Okay. Yeah, so I'll rewrite the observation. Actually, I'm in the hostel right now, so people keep coming to the room. So anyway, observe that triangle EDC is isosceles. Okay, implies DE is equal to EC, right? All right. Okay, so now there is one more step to go. Step 3 is essentially my cyclic quadrilateral step, as I would like to call it. Yes. So what do we do in this step? In this step, we essentially find a cyclic quadrilateral, as simple as that. So looking at the figure, you can spot a quadrilateral, right? So the quadrilateral that you can spot is ADEB, right? Is it cyclic? Yes. We are lucky enough to have this quadrilateral to be cyclic. See, angle B plus angle D, angle ABE plus angle AD is equal to 180. And so is angle BAD plus angle BD. Okay. So I have my cyclic quadrilateral as well. So again, what I was saying before the interruption is that what do I need? I already have BD equal to BE. So I just need AD to be equal to EC, right? And I already have DE equal to EC. So this I have, this I don't have. So if I can somehow show that AD is equal to DE, then we are done. So this is my target, okay? So if I do that, what happens is, so in order to show that, what I will do is I'll just join this, okay? I mean, it will be a little bit messy, but I hope you can all see. So this is a cyclic quadrilateral, okay? So let me essentially draw a circle around this. Okay, now I guess you can visualize clearly. So if this angle is 20 degree, this angle is also 20 degree. Okay, angle subtended by the same chord D. All right. So, and also similarly, if this angle is 20 degree, then this angle is also 20 degree, right? So see that again, one more beautiful piece of information that we have extracted from this problem is that observe that triangle ADE is isosceles, which implies AD equal to D. Okay. So step 4 is just unifying our steps. So from the previous steps, we obtain. So first thing that we obtain is AD is equal to EC. And this is the second thing actually. The first thing is BD equal to B. And the second thing is AD is equal to EC. Okay. So summing up, we have our result, which is BD plus AD equal to BC. Okay. So yeah, I almost similarity congruence was not explored, but more or less the other 3 principles of solving geometry problems from scratch. I mean, there is a whole lot of things you can do from starting from pre-IMO level problems to IMO level problems using this 4. Okay, so I hope you enjoyed the demo lecture session that we had organized today, and this was to actually let you guys know that what we are trying to do through our workshop, and also so that's all for today. Then I hope you all had a good session, and we all really enjoyed teaching you guys too. Thank you. Good night. Orko sir, are you there?
Yeah. So I'll just thank you, Shotim, and all for such a nice session. And so I'll just end the session then.